So, what is this negative sign here telling me? Well, compression is what happens when V1 is greater than V2. Right? So when I go to a smaller volume, if I go from a larger volume to a smaller volume, then this integral, again, the boundary work is going to be the integral. If it's in the out direction, it's going to be the integral from V1 to V2 of pressure with respect to volume. So if this is the larger quantity, then this is going to generate a negative quantity. Your boundary work in the out direction is going to be negative. So it's technically work in. I guess I'm off the screen. I apologize. So this is technically work in. If it's compression, it's technically work in because it's the opposite of work out. So you can do this a couple of ways. You can either plug it back over here into your first law equation, right? This guy, you can plug, this is a work out term, and if I plug it in as a negative work out, so I get a minus a negative 22 kilojoules, then it ends up becoming positive, and you treat it mathematically the same as a work in. So you can do it a couple of ways. That's what I normally do. Say, well, I always compute a boundary work as a work out term, and if it picks up a negative sign, as this one does, that just tells me, you know what, it's actually compression, not a big deal. Plug in as a work out, it picks up the extra negative sign, and it turns back into positive, just like a work in term. Now, if your system is expanding, if you have expansion, that is where you're going to a larger volume. And you're starting at a smaller volume, going to a larger volume. Then your boundary work in the out direction is going to be positive. If this is bigger than that one, this quantity is positive, you're going to get a positive boundary work out. Expansion is actually work out. If I'm running an engine, that's what I want. If I'm running an engine, I'm putting heat into it, and I want that to cause expansion. That causes work out. So this is kind of the traditional sign convention. As I mentioned earlier, if you look at this and say, Steve, it's going to a lower temperature, so that means it's being compressed, I'm going to compute the work in, so I'm going to actually switch the sign on this integral. That's fine. If that doesn't confuse you, go for it. I try to keep it simple and just say, let's always compute work in the out direction. That's from V1 to V2. And then we'll take care of the sign afterwards. So this negative sign means it's actually compression work. I can either plug it in to my first law equation back over here. I can either plug it in as a negative 22 kilojoules here, or I can plug it in as a positive 22 kilojoules in the work in term, and the signs end up taking care of themselves, which I think we'll see coming up next. Right? So these are my notes. Graphically, we've already drawn this. So this would be a little closer to, if this was an actual test problem, this is probably what it would look more like. This is just an additional step. I've got a weighted piston, same steam contained in a weighted piston, 0.3 kilograms, initial pressure and temperature, determine the heat transfer from the cylinder given the final state. Okay, so let's work this one. So again, and I'm going to go kind of quickly here. Another example. Find the heat out. Same givens. Mass 0.3 kilograms. Pressure 1 is equal to pressure 2 is equal to 1 megapascal. T1 is equal to 400 degrees C. T2 is equal to 250 degrees C. This is water. Okay. Now again, we know it's a piston cylinder. We say, all right, what are some good tools to find heat, to find this heat out term? Well, first law, first law is kind of my go-to. Anytime I'm looking for any energy term, I'm probably going to go to the first law, especially heat. That's kind of our main tool. So we say, to write a first law equation, again, that is going to be in minus out equals change. And you say, all right, well, what comes into the system and what goes out of the system? Well, I don't see anything coming into the system. I do know it's losing heat because that's what we're looking for. And there is also this, anytime I've got a piston cylinder or any type of system where the volume can change, I'm going to have a boundary work term. So that's an additional energy that's either going out or, in this case, it's actually coming in. But we're going to treat it like it's going out. Okay? So if I treat this boundary work as an out term, so again, add the in, subtract the outs. So I've got a heat, so minus a Q out, minus a boundary work out. Those are the things crossing the boundary. Those are the energies crossing the boundary. That equals the change. This is a stationary, closed system. So the only thing changing is going to be the internal energy. Okay. Now we've found from the previous example, if you're just joining us, look at the previous parts of this video. In the previous example, we've found that the boundary work out was actually minus 22.16 kilojoules. So we already know this. This is known. We did the integral of pressure with respect to volume and got this done. I know the mass. I'm looking for the heat. So I've got one equation. I need one unknown. That means I need these other two. And just like we did in the previous solution, I can, given the properties, so again, somewhere below in your solutions here, write properties and say, well, knowing P1 and T1, that's enough information to find U1. And knowing P2 and T2, that's enough information to find U2. I don't know if I've got these. I think we'll have to... Yeah, I don't have these. So, pause the video. Go look these up real quick. Make sure I'm not telling you something that's wrong. I apologize for the pause there. Alright, 1 megapascal. So look in your property tables. At 400 degrees C, I've got a U1 here of 2957.9 kilojoules per kilogram. Again, you need to be able to look these up on your own. If you're struggling with this, let's get some help. You will not proceed well in the rest of this course if you don't know how to find these properties in your book. Okay, let's get that taken care of now, because you're really setting yourself up for failure later if you don't know how to do this yet. Okay? This is, anyway. So now, I've got these properties. Again, if you're getting something different, please leave that in the comments. And if you're getting something different, look in the comments. See if somebody's already posted the... I will get those wrong sometimes because I'm doing them quickly. So if I solve for Q out, that is equal to, let's see, maybe M plus... Okay, so I'm going to say M U1 minus U2 minus the boundary work out. I think that's right. Okay, there's a lot of negative signs going on there. So before you post in the comments, write this algebra out. Make sure you're comfortable with that. There's a lot of negative signs getting moved around there. So this is my mass. That is 0.3 kilograms times U1 2957.1.9 2957.9 minus 2710.4. Now, if we run out of time, write an answer down in the comments. Okay? Minus a negative 22.16 kilojoules. Sorry, I know that's too small. Okay? Let me just write that. Q out is equal to, now let's just do this quantity. I got about 5 minutes. We got time. Let's make sure I'm on the screen. I'm not getting a glare. Awesome. Okay. So let's write this out. We got 0.3 kilograms times 2957.9. Now, Let's do the inside first. 2957.9 minus 2710.4. Do that first. Multiply by 0.3 because I'm just using a simple calculator out. Okay, so this quantity here is 74.25 kilojoules. And the other quantity, this is minus the boundary work out, and that is a negative 22.16 kilojoules. You see what I did there? I left it as minus the boundary work out. It's coming in at minus 22.16, so it's minus a negative. So it's actually going to be plus 22.16 kilojoules. And please forgive me if that is wrong, because I've got 500 things going on trying to make this video and trying to get them all right. So if you're getting something different, leave it in the comments. Let's have a discussion down there. And if you're getting something different, look in the comments. And let's make sure we will kind of iron it out down there. But that's my best guess trying to do this quickly. What do we do with that? Are we done? How do we know if we're done? We go back up here and we say, what the heck were we looking for? We were looking for the heat out. And I found a quantity for what I think is the heat out. So I think I'm done. Right? I've got a minute or two here before my timer goes off. Let me suggest something to you. If you're using Chegg or Slater or something like that, I don't mind that if you're using it responsibly. Let me tell you this. If you can't get yourself to this point, right? Have your equation set up, go back and be able to do this part, right? Be able to find your boundary work back over here, okay? And then know how you're going to get to these properties. If you can't get to that point, you're not ready, and this is the point where you look at another solution. Does that make sense? If you're looking at the solution before you get to this point, you are cheating yourself. You're going to struggle on the exam. You're not actually learning how to solve these problems, which is the goal, is to learn how to solve problems. Okay? All you're doing is plagiarizing. Maybe paraphrasing without giving credit, which is still plagiarizing. And I hope that makes sense. If that doesn't make sense, leave me a comment. Let's talk about that. But seriously, or send me an email. Let's talk about that. This is the point you got to get to before you look at a solution. Now, if you get this far, then you could go look at another solution, because then you got to do some pretty hard grunt work to get to an actual number. And if you want to say, hey, I don't want to go too far down this road before I get an actual number, I want to make sure I'm on the right track. Okay, that's fine. Check another solution at this point, but don't check it before this. Force yourself to get it. Steve, that's really hard to do. That's a lot. I don't know how to do that. Try. That's all I can tell you. Is keep trying. Keep practicing. That's how you're going to get to where you're actually going to be able to do this and then survive later courses in engineering. If you can't solve problems, that's really what we're trying to teach you how to do, is solve problems that you've never seen before, because that's what people are hopefully going to pay you someday a lot of money to do, is go solve problems that nobody's ever solved before. How do you do that? You learn how to solve problems. How do you do that? You do a lot of practice. And this is just kind of the first step in that. Okay? I hope that helps. Let me know if something's wrong, something looks out of place, you have questions, send me an email, leave me a comment. Let's figure this out. Okay? All right, guys. Good work on the test, and I will see you on the next video.